Good morning, ma'am. This is me, Agastya Goyal from Section CP, and today here I am about to speak on the topic electric aircraft propulsion. The concept of electric aircraft propulsion was first studied by two French brothers in the year 1883, Gaston and Albert. What they did was basically they installed a 1.5 HP Siemens electric motor in an airship, which was a motor that developed an airspeed of 7 mph during a flight that was more than 1 hour long. Current aircraft propulsion methods primarily use gas turbine engines that solely depend on burning an air-fuel mixture for producing the required thrust. In a gas turbine, the gases undergo various thermodynamic processes, where mechanisms energy is converted into thermal energy, followed by heat rejection that creates a low pressure. This allows fresh air to flow in, which is combined with fuel. The following air-fuel mixture is ignited and allowed to expand, increasing its velocity across the turbine section, forcing it to strike the turbine blades. This causes the spinning of the disc that they are attached to, creating useful power. Only 40 to 50% of this useful power is used to power the gas generators in the gas turbine engine. The remaining power is used to typically power an aviation, whose applications are thrust in a turbojet, driving the fan of a turbofan, rotor, or accessory of a turbo shaft, and gear reduction and propeller of a turboprop. Electric aircrafts driven by electric batteries can provide a very high overall efficiency on energy flows compared to current propulsion methods. Also, the electric aircraft propulsion is very cost effective. With further improvements from the steady ongoing developments and technological advantages, the electric aircraft systems could be a boon for a successful future aviation sector. This is because electric aircrafts could create a less noisy, more greener, and more effective aviation sector in future. With respect to current developments in technology, with the growing emphasis on sustainability and the need to reduce carbon emissions, electric aircraft has emerged as a promising solution for the future air transportation. Now let's talk about hardware. Electric energy source and energy storage systems. The electrical component of electric aircraft propulsion is the electrical energy generating and storage unit. Current research areas focused on electrical power generation by hybrid propulsion units, PV modules, and alkaline medium fuel batteries. Batteries and superconductors are the two important hardware technologies of electrical energy storage and delivery units. Electric motors and their control systems. Example, YASA 750R motor. Power electronics. The basic principles of power electronics are power conversion, switching operation, pulse width modulation. Passive components like capacitors, inductors, and resistors. They are essential for filtering and adjusting electrical signals and also for providing reactive power support. Propellers, that are fans, are made of lightweight and durable materials like aluminum and other composite materials. Thermal management systems. Components like semiconductors, devices, and passive components generate heat during operation. Hence, effective heat management methods are required to dissipate heat and cool the systems, as thermal stresses and temperature variations can hinder effective performance and reliability of the power electronic system. Thus, advanced cooling technologies and thermally stable and exotic materials are very much required. Now let's talk about software. Flight control algorithms. Flight envelope protection. Flight envelope protection algorithms ensure the aircraft operates with safe flight envelopes, preventing uninvented or exceeding design limits. Autopilot and stability control. Advanced algorithms assist in autopilot functions and stability control, maintaining safe and stable flight. Motor and control algorithms. It follows up with field-oriented algorithms. They optimize the performance of the motors by aligning and stator the current with the rotor magnetic field, improving control and efficiency. Direct torque control. They control the torque and flux of the motor, providing presence control without the need of complex transformations. Battery management system algorithms. State of charge estimation. SOC algorithms estimate the remaining energy in the battery, thus optimizing energy usage and preventing overcharging or overdischarging. State of health monitoring. SOH algorithms assess the overall health and degradation of the battery over time. Energy management algorithms. It follows up with optimal power flow. OPF algorithms guard the distribution of electrical power among various components such as the motor and auxiliary systems to maximize overall efficiency. Load shedding algorithms. In cases of power constraints, load shedding algorithms prioritize critical systems to ensure the aircraft's essential functions are maintained. Real time monitoring and control algorithms. It follows up with closed loop control. Real time feedback loops and control algorithms continuously adjust parameters to optimize performance during flight. Adaptive control. Adaptive control algorithms adjust systems parameters in response to changing conditions, ensuring optimal performance. Now let's talk about design, basically the construction and working. In comparison with the current propulsion systems that are entirely built around an internal combustion engine, electric propulsion designs utilize an electric motor. An integrated power propulsion system consists of critical components like motor, controller hardware, and software, gearboxes, and cooling systems. This system is known as electric propulsion unit. As we as and when the battery technology advances, electric aircrafts will need both batteries and other power sources like fuel cells and ultra efficient generators. Currently, there are three types of electric propulsion designs being considered as aircrafts, and that is the hybrid electric, turbo electric, and all electric. Now let's talk about the hybrid electric aircraft propulsion. Hybrid electric aircraft propulsion can be designed in two ways. Combination of a traditional turboprop engine with an electric motor powered by batteries in a parallel hybrid configuration, and the other one is combination of two traditional turboprop engine with an electric motor powered directly from batteries or voltage generators, which are in turn propelled mechanically through the turbine shaft. This design is also called as series hybrid configuration.
Let us have a look at turbo-electric aircraft propulsion. The turbo-electric aircraft design has electric motors as the only source of thrust for the aircraft propulsion. What happens is a turbine engine generates the required kinetic energy for the turbine shaft that propels an electric generator to produce electrical power for the fans. The fans are driven by separate electric motors. Let us have a look at the block diagram to have a better understanding. This design provides aircraft designers with more choices in choosing the number of fans as well as the location of fans. By looking at the block diagram, we get to know that different number of fans are arranged to separate motors, which are connected to a single generator that generates electrical power. This leads to more efficient aircraft designs with a higher performance rate of the propulsion systems. Having a look at an all-electric aircraft propulsion system, it uses high-density batteries as a power source that store electrical energy. These batteries power the electric motors, which in turn rotate the fans or propellers to create thrust. All-electric aircraft propulsion is the only configuration which eliminates or removes any need for a turbine engine and its fuel delivery system. Both are present in hybrid electric and turbo-electric designs, hence we can overcome the cost with all-electric aircraft propulsion. The current batteries used in all-electric aircraft propulsion face difficulty with their energy density for big aircrafts, and research is going on to address this issue. This limits all-electric aircraft propulsion methods to shorter flight ranges. Looking at the key benefits, since it is all electric, obviously zero emissions, it eliminates the need of a turbine engine, hence cost effective. The motors are more efficient and it reduces noise pollution too. So let us have a look at each one of them individually. Under generation of electrical energy, we'll first have a look at photovoltaic modules or the PV modules. The evolution of present PV photovoltaic technology dates back to 1954 when silicon PV cells were developed in the US. At present, many various photovoltaic technologies exist, including silicon cells, organic cells, polymer cells, thin layer solar cells, etc., that are reaching an efficiency of almost 44%, which is 30% more than the present efficiency. But the structure and the cost efficiency of silicon PV cells make them the most reliable ones for PV modules till date. An important performance measure of PV cells is their efficiency to convert the captured solar energy that is usually expressed as a percentage of the generated electrical energy in comparison to the solar energy of the irradiation. Having a look at fuel cells. Fuel cells are similar to electrical batteries in the manner that they produce electrical energy from a chemical reaction. But when compared to a typical combustion engine, the main difference is that the chemical energy of a fuel cell is released in the form of electric current instead of heat energy, which enables the fuel cells to provide high energy efficiency with lower emission levels. Most commonly used fuels in fuel cells include hydrogen and oxygen, while certain fuel cells operate on methanol or methane too. A main advantage is that fuel cells achieve high specific energy levels than the lithium-ion batteries which are trending today of up to 1980 kilojoules per kg. Factors limiting the future fuel cell applications in aircraft propulsion are that they require the onboard storage of pressurized hydrogen or the fuels in flight, when we have a look at the storage of electrical energy, we have SMES, that is a superconducting magnetic energy storage. SMES is a method of storing electrical energy through generating and sustaining an effective magnetic field. SMES demonstrates high efficiency, that is of up to more than 95% of charging and discharging, making it most suitable for high power short cycle applications. Also, there is improvement in the engineering of superconducting materials, especially in increasing the critical temperature, the point at which the superconduction transfer takes place. In SMES, when electric current flows through cryogenically cooled superconducting winding, it continues to flow even with the voltage input being removed from the terminals, and hence the magnetic field can be sustained. Thus, it becomes an efficient method of storing electrical energy through the sustenance of an effective magnetic field. Having a look at superconductors, superconductors can generate much higher levels of specific power with the advantage of lower specific energy capacity. The electric double layer capacitors or the EDLCs are the most common type of supercapacitors. When it comes to aircraft propulsion, the maximum power demand arises during takeoff, which can be satisfied by supercapacitors effectively and efficiently in a relatively shorter time. EDLCs, as I mentioned earlier, EDLCs are the most common type of supercapacitors which store electrical energy in an electrostatic field, and they have a very long shelf life or a service life capable of operating for millions of charge discharge cycles at faster rates when compared to the typical batteries which have a very small number of discharge or charge cycles like around 1000 to 1500. Coming to the results of our project on electric aircraft propulsion, around 50 to 60 years ago, it was generally considered that was when electric aircraft propulsion was not sustainable for aircrafts. It was believed because no electric motor was capable of producing the amount of power required to generate enough thrust to lift the total weight of the aircraft in those days. That because the weight increases due to its pilot, the electric motor, and the various batteries that are necessary to supply the power to the propulsion system. Also, the advancements in technology have brought back the topic of electric aircraft propulsion into the light of research now in the late 2000s, currently 2026. The safety of electric batteries is a considerable issue, an example of which is the failure of lithium ion batteries aboard the Boeing several years ago. It was believed that no electric motor was capable of producing enough thrust, but today's research has made this a booming field in electrical energy. The most advanced work, some of which were finished with certification and project implementation, concerns small aircrafts for GA and air taxis. The work on the application of alternative aircraft propulsion systems that include electric power in the commercial aviation is primarily led by design officers of few of the largest aerospace organizations in the world, such as NASA, Airbus, Boeing, Cessna, etc. At present, there is research in the field of aerospace applications of electric propulsion carried out at around 70 research centers and design engineering units. Many of them are third-party operations related to aviation, and so far the first and the only all-electric aircraft was certified in 2020 by the EASA. It was a two-seater trainer, and the electro design was built by Pipistrel of Slovenia. These are few references. We had referred to a few articles from NASA, from Transformative Forces in Electric Propulsion, Honeywell, Wikipedia, etc. Thank you.